Alright, so welcome to our next video here. In this video we're going to talk about the stack more, and we're going to focus in on arguments and local variables. We're going to take a look at the stack again and see how it's being changed through function calls, how it's being used for function calls, and then as well as how we create space on the stack for those local variables. So talk about local variables, and local variables are very commonly going to be stack based. That is, that we're using that address space for the stack in order to allocate that space and use it for locals. So we'll take a look at an example with that, but typically we think of a local variable as something that we define, a variable that we define within the scope of a function. So if I say inside of main int a equals 32, then I'm declaring a variable locally. Globally scoped, those are declared generally speaking outside of a function, and so we don't generally use the stack for those variables. What will happen then, and what we need to understand, is the stack layout in order to know how to reference those variables, because what you're looking at, and you've seen that already in a lot of the disassembly and the programs that we've been looking at, is EBP minus and EBP plus, and we're using that base pointer in order to reference offsets on the stack to get at arguments as well as to get as those local variables. So what we saw, we talked about the prologue, and what you have with the prologue is you generally have a push EBP and then move into EBP ESP. And I said that's really your quintessential prologue. There's another piece to it, another component, and you generally will see this when there's locals. You might see a sub, a sub and then some hex number. So let's just say 8 hex, right? That subtraction, what that's doing is, sub ESP and then a value, right? Instruction right here. And what that's doing then is it's taking our stack pointer, ESP, and it's moving it. It's moving it to a lower address. So we're allocating more space on that stack so that we can use that space for those local variables. How the stack then is modified is that we have, at this point in time, after the beginning of our prologue, EBP and ESP are essentially pointing to the same place. They're pointing at the top of the stack. When we subtract 8 from ESP, ESP points to a different location now. And so we can use EBP and offsets relative to EBP in order to access the arguments, access the local variables. So that is how we're going to be using it, and that's how you'll see it used very commonly in a lot of the programs that we're going to look at. Remember that we typically deal with the stack. We do 4-byte increments. We're talking about 32-bit, and we do that. You see that for memory alignment. And so subtract ESP is probably going to be a multiple of 4. 4, 8, C, 1, 0, 1, 4, 1, 8, right? All in hex values. So we're generally going to see that in 4. Pushing and popping, another way that we modify the stack. That's also done 4 bytes at a time. Push, we push on 4 bytes. Pop, we pop off 4 bytes. We move ESP up and down in 4-byte increments. Okay, once we have a reference to that data, right, we'll have, you'll see commonly EBP minus 4, one way to get to the data, EBP minus 8, another way to get to that data. I'll diagram all this out in a moment. But if we want to be able to move data maybe from local to a register and manipulate it, then you'll see these type of instructions right here. Okay, so remember, EBP minus 4, that'll move whatever is in that location into EAX, right? It'll move that data, so it'll take EBP, whatever address that is, and subtract 4 from it. And then these will allow us to dereference, so these brackets here. So we'll move whatever data is in EBP minus 4 into EAX, right? Once it's in EAX, we can do things with it, increment, decrement, other operations. Once we're done, we can take another move instruction and move whatever was in EAX back into EBP minus 4. Again, we need to dereference that location in order to store data at that address. If we needed the address for EBP minus 4, which sometimes we do, then we'd have to use the LEA instruction, which is load effective address. That would give us the address for that location and not the data. Okay, so there's a little bit of there's a big difference between the two. So let's look at an example. Here we have a pseudo C program, and let's just assume, so that we can focus on the locals here, that we have a prologue, so that when we look at this in assembly, we have a prologue, we have an epilogue. Okay, X, Y, and Z. So these are all local variables inside of some function. All right, we'll just say this is inside some function here. Okay, so how does this look? Well, we know some things about the stack already because these are integers. They're going to be 4 bytes or 32 bits. Okay, integers on most platforms, 32-bit platforms, are going to be 32 bits. So we know that we're going to need in our function, in our stack, 4 plus 4 plus 4, right? 8C. So we have C hex. That's the number of bytes that we need inside of on our stack in order to support these local variables. Okay, here is some assembly. So let's say we compile that program and then we disassemble it using IDA. Okay, this is likely what we would see. Okay, again, we're going to assume that we have the prologue up here. We've already talked about. We have epilogue down here. And now you can see, here's our subtract from ESP 0C hex. All right, so let's diagram out some memory to help. Okay, we have higher addresses, lower addresses. Okay, we'll assume this was a function call. So there doesn't look like there's any arguments. So when that's called, we'll have our return address pushed onto the stack. We have the prologue, so we're going to push EBP. So we're going to have old EBP here. Okay, at that point in time, when the prologue's done, this is where EBP is pointing, right here. Right, that's move. We push that on, and then we move ESP into EBP. So ESP and EBP are both pointing to this location. Now we subtract from ESP 0C hex. So this is 4, this is 8, and this is C. Okay, so now we've allocated space on the stack for those local variables. And if we go back, those were declared int x, int y, and int z. So now we have space on the stack for x and y and z, right? And when we're done, because sub subtracts from ESP, ESP is now pointing right here. Okay, so how do we reference? How do I know, and how do I get access to the space on the stack for x or y or z? Well, now we have those offsets. Okay, so EBP, higher and lower addresses. EBP to get to x, EBP is pointing right here. So if we reference just EBP, we'd have the old value of EBP. We don't really care about that. So EBP minus 4, that gives us x. EBP minus 8, that gives us y. And EBP minus c in hex gives us access to z. Okay, let's say that this function had arguments. They would have been pushed on before the function call. So let's say this is an argument, right? EBP plus 4, that gives us the return address. EBP plus 8 gives us access to the arguments. See, and that's what you're looking at when you see EBP minus, right? The stack pointer can change. It can change throughout the function execution of a function. Using EBP makes that a little bit more stable, and that EBP isn't going to change until the epilogue of the function, until the function's done, in which case then we're done with all those local variables. Okay, so if we go back and look at that example, you can see that we defined x, y, and z 0, 1, and 2. Okay, we initialize those values. So EBP minus 4, right here, that's x. We move into that location 0. EBP minus 8. Okay, I see I've subtracted or calculated that offset from EBP correctly. 1 gets moved into minus 8. 2 gets moved into EBP minus 0C hex. Okay, and then just like the previous example, if you want to work with those, with the data in those locations, then you need to dereference. So you can see with this move instruction, EBP minus 8 is going to dereference and move that data into the EAX register. And so now you can use that in order to manipulate that data, and that's what you're seeing with those instructions. All right, some things to know. Moving and working with the stack is slower than a register, and so what can happen from time to time is that compilers and optimizing compilers, this is important, is that they will sometimes optimize your code to not use the stack. If you have a function and let's say it only has 2 arguments, well, it might just use 2 registers in order to pass arguments to that function instead of using the stack. So you need to pay attention to how a register is being used right before a function call, and then when you're looking inside that function, see if that same register is being used, because it might be passing an argument via a register instead of a stack. the bottom line is that not every program will use a stack to pass arguments. And to also use those for local variables. A register might be used depending on the program, depending on the compiler. Okay, there are some shortcut instructions. Generally you don't run into these with IDA, but you might see them out there, enter and leave. They're just shortcuts for the prologue and the epilogue. And so what enter will do is it'll do push EBP, move EBP ESP. What leave will do is it'll do move ESP EBP and pop EBP. So you can see here, there is our epilogue right here, and here is our prologue right here. Right, so those are just shortcuts for that. The actual instruction, this is really the instruction. So you either have leave or you have enter 0, 0. You can see that that instruction is 2 operands. We'll talk about those on the next slide here. What is the benefit? It's easier to write. The downside is that it's actually slower than doing by hand, and so a lot of compilers don't use that. So that's why oftentimes when you're looking at, especially the disassembly of a program, you don't see enter and leave. You see push EBP, move EBP, ESP, and the epilogue as well. You see that, spelled out. Okay, so what about enter? What about those arguments? The second one is pretty much never used, so you don't have to worry about that one. The first one, though, is used to allocate space on the stack. So think about, we have in the prologue, we have the push instruction and then the move. Well, that first operand would give us a sub, or subtract. So we'd say enter 8, that would turn into push EBP, move into EBP ESP, and then subtract 8. Well, subtract ESP 8. Right, that's allocating space on the stack. So you could see that, you could use that as well if you'd like. Okay, what does leave do? Talked about that already. Resets ESP to EBP. So it moves EBP into ESP, or epilogue, and then it restores the old value of EBP, which is pop EBP. Right, we got to get that off the stack. You still need a return. So you might see in a function, in a program, you might see leave and then ret. Right, but you still have to ret. This is all right here and right here. This is all that leave is doing. So you still need a return. Question, do you have to adjust for something like this? Let's say that we enter 100, 0. So we've subtracted 100 bytes on the stack for local variables, for local use in that function. Do we need to adjust for that when we leave? Well, the answer is no. We don't have to adjust for that. And the reason that is because when we get ready to leave, when we execute the epilogue, and this isn't just specific to the leave instruction, but no matter where ESP is, when we're ready to return from a function, if we move EBP into ESP, no matter where ESP is, that essentially deallocates all the space on the stack, so this sub 100, and moves it back to where it was at the beginning of the function, the beginning of that prologue. It turns it back to the base. So we don't have to worry about things like that. We can just say move into EBP ESP, pop EBP, and now that return address is right there on top of the stack, ready to go. Okay, how do you modify the stack? Important to understand. You can do that 2 different ways, implicit, explicit. Implicitly, pushes and pops. Remember, pushes and pops. Push subtracts from ESP by 4 bytes. Pop adds to ESP by 4 bytes. Right? Because remember, we go from higher to lower with stack. Call, because when we call an instruction, when we call a function, that's going to push the return address onto the stack. And return, because return is going to pop what's ever on top of the stack and move it into EIP. So all these methods here are going to do it implicitly. We can also modify the stack explicitly. You saw that in the prologue. You saw that when we allocated space on the stack for locals. We can add to ESP, we can move to ESP, we can subtract, and this should not be and. This should be add. All right, there's a variety of ways. I guess and would work, but we also add. We can change where ESP points to. We have to be very careful though, because if we modify where ESP is pointing to, it can disrupt the flow. Remember, the stack is very important for the flow of our programs because that return address from function calls get pushed onto there, and so we can mess that up. We can cause a program to crash or the flow to get corrupt. Okay, ways to modify ESP. We already talked about that. Every once in a while you see an ESP-based stack. EBP is much more common, but if you're looking at or you see ESP being used, and you will, it's going to look very similar. Right? You might see ESP plus some value, ESP plus some value, right? ESP plus some value. Because remember, on our stack, If this is our stack, this is our memory space, addresses are higher to lower, and ESP is always going to be pointing to the top of the stack. So if we want to reference something on the stack using ESP, we have to go to a higher address. So we have to say +4, +8, plus C hex, right? We won't do negative, because negative would take us into address space out here we don't have access to. Okay, so if you ever see ESP being used to reference the stack, and you will, then it's always going to be plus some offset. And this is what I mean by offset. Plus and then this value, right? It's an offset from this base address, that base location. Okay, a little bit harder to read. Things can change. We can see through the execution of a program that the stack can grow, can change. And so ESP +14 might reference a certain location, ESP +4 might reference a certain location at this particular time in the function. Later on in the function, if the stack changes, maybe now it's grown, and so now that same location is ESP +8, right? If this is +4 right here, well, what if the stack grows? Right? What if there's another push later on in the function? Well, now to get to that same location, it's just become ESP +8. Okay, so it's a little bit harder to read when using ESP, so that's why EBP is much more common. Okay, let's look at one more example. As far as stack intro, so C code as well as an executable. Okay, what I'm going to try to do, oops, bring this over, and let's diagram this out as we go. Okay, so get ready here, draw another stack. Higher to lower. Okay, and then we'll have two things that we care about, EBP and ESP. And we're just going to trace this through to the point where we're talking about those local variables. Okay, here's the source program. I have one function called func1, takes 3 arguments, and just does some arbitrary math. So it sums them together, adds some locals, not all that important. Inside a main, all main does is calls that function and pushes those values on. So what does that look like in IDA? Okay, well, you can see here, here's our prologue. Okay, we're in function main. There are no locals in function main, so you don't see a sub after this last instruction here, move EBP ESP. Okay, 3, 2, 1, those are essentially hard-coded in the program. So you can see push 3, push 2, push 1. So with our stack, how that's going to look, we push 3, then we push 2, and then we push 1. Okay, another very important thing to notice, 1, 2, 3, 1 is the first argument, 1 is the last thing that we push on. Right? So they're pushed in reverse order. 3 is the very first thing pushed on. Okay, now we have to call the sub. So that's going to call function 1. So when that happens, the call pushes the return address on. So I'm going to put space on there, call that return. That is the address right here. So if I turn on line prefixes, what is really getting pushed onto the stack is this address, 40103E. Okay, that's the value that's going to be right here for this return address. Okay, let's go check out that function. So here we can see, here's our prologue, plus we have stack space being allocated, right, because we have some locals. So push EBP, so our stack's going to change again, because we're now pushing on to the stack, push instruction. So here's old EBP. And now we sub, okay, then move ESP into EBP, and then we sub 8 from ESP. So there's 4 bytes, there's 4 bytes. Remember, each one of these blocks that I'm drawing represents 4 bytes. Okay, so EBP pointing right here, ESP pointing right here. Okay, that's how our stack's laid out. Now we're ready to, work with those local variables inside the function. We can see in function 1, sum and x, we have 2 local variables. 2, so 4 and 4, 8. That's why you saw sub from ESP 8. We can also, with IDA, see that we have var4 and var8, right? And that's where those are coming from. That's how IDA is trying to identify for you that there are local variables. arg8, arg4, arg0, var4, var8. So we can see that IDA is telling us that this function has 3 arguments and 2 local variables. Okay, now, so in order to reference those local variables, okay, EBP is pointing to this location on the stack, the old value of EBP. So, higher to lower, we have to subtract from EBP in order to reference those locations, -4, -8. That's how we can reference the stack space for those 2 local variables. Okay, we can figure out which ones they are if we needed to, if we want to match those up to the source. So we can see if we go back and look at the source in function 1, sum equals 0. Okay, if we look at IDA, we can see that 0 is getting moved into EBP plus var8. The next one, 63 hex, which is 99 and base 10, is moved into var4. Okay, so based off of those moves, if we wanted to, we could go back to this diagram here and say -4 has got a value of 99, so that must be x, and -8 has a value of 0, so this must be our local sum. Okay, space has been allocated for those. And of course, we might want to rename those. So I said -8 is sum, and that is x. Okay, the other thing that you'll notice here when looking at those variables in IDA is that you have EBP plus and then that variable name. What is that variable? Well, it actually points to this dword pointer -8, dword pointer -4. And so don't be confused. This isn't saying that we're adding a positive value. What we're actually doing here is it's saying EBP plus -8, EBP plus -4. And so that's how these offset values match up with our stack and how our stack's being laid out for arguments for local variables. Okay, same with these arguments, arg0, arg4, arg8. In this case, if we want to reference those values, we have to go to a higher address from EBP. Okay, so we want to add to it. So this is, EBP is right here. This is +4, +8, plus C, plus 1, 0. And that's how what these arguments map out. 8, 0C, 1, 0. So we can see that that's argument 0, that's argument 4, or I'm sorry, argument 0, argument 1, argument 2. Right? EBP plus, and in this case it is actually a positive value. But it's just providing us a mapping and ability to rename those. This is how our stack's lined up. This is how our stack's allocated and being utilized for this particular function. Okay, so just wanted to point those out. Okay, use these. They're very important. They help you to understand arguments, local variables within the stack, within this function on the stack. Okay, but from EBP, locals are all negative. Right, so EBP plus sum is actually a -8. EBP plus x is actually a -4. Okay, so that's how you see. So using EBP to reference those different offsets, calculate those different offsets to reference those variables on the stack. That's it. Okay, so we kind of went through in the last video how the stack unwinds essentially, and then how the function returns from here. So we won't go through that again. The important part from this video was just understanding these offsets. What I really want you to be able to do after this video is to look at these functions now and go, okay, I can understand EBP plus and these values, how they map up to these, how IDA is displaying arguments and locals for you, and then how that relates to the stack. And it's always helped me to be able to visualize this, so hopefully that helps you as well. If you have any questions, let me know. Otherwise, in the next video, we'll start talking about arrays. Thank you.